Hello. So our building design, we understand that, has been mentioned before, there's a lot of faults with the softwares. This allowed us to create two models. We used a Revit and robot structural analysis combination, as well as a ETABS model. We used these two models to validate each other. However, when they were validated, we trusted ETABS more because we could consider things such as the soil springs on the foundation walls, as well as the footings. However, we use Revit for a lot of our detailing and our rebar schedules. Now, for the gravity loads, majority were actually the dead loads because we have a very tall building and it's made of reinforced concrete. We use the NBCC guidelines for live loads based on the occupancy, such as residential, fire exits, and balconies. And then we had superimposed dead loads, which were the cladding weights on the outside, as well as the weights of the ceiling and floor materials. For the lateral loads, we had a wind report provided to us from Gradient Wind, and we imported those loads into ETABS with these 24 different NBCC load combinations, as well as we used the auto lateral load for ETABS to produce the seismic envelope with the NBCC load combinations. We determined that the base shear in the X direction was governed with seismic for 4,900 kilonewtons, and the unfactored base shear in the Y direction was governed by wind with 5,000 kilonewtons. Now for the moments, the unfactored base moment about the Y axis was governed by seismic with 582,000 kilonewton meters, and the unfactored base moment about the x-axis was governed in wind about 559,000 kilonewton meters. As well, the wind introduced unfactored base torsion of 25,000 kilonewton meters. We input all of these into ETABS and with these 16 different load combinations, and we use them for our analysis and design. Now I'll pass it off to Michaela for slab analysis.
Thank you, Matthew. This project included 15 variations to the slab layout. To prevent loss of profit, some of the design variations were limited. This included the thickness of the slab, which allowed us to maximize the amount of stories we can build. In the podium and parking levels, the space must be maximized, including more parking and revenue. Due to this, the columns and walls needed to be offset, creating complex layouts. The following flow chart was used in the design process. The preliminary dimensions and load combinations were inputted into our ETABS model. We run the analysis to identify any modifications required, and we added it onto the design to include these modifications. We bring this data into the Excel, or we could also export it into SAFE and use the finite element-based design for complex layouts. However, to validate the slab designs, we opted to hand calculate the column offset and identify one-way or two-way slabs. This data was exported into Bluebeam, where the design strips and middle strip sizes were established. These were used in SAFE to run a design strip analysis. The design was then checked against the CSA A23.3-14 requirements, and if it did not pass, we went back to modify the design. If it did pass, we went forward and with manual calculations to validate the design where applicable, and proceeded with safe scheduling for the rebar. This process was repeated for all other layouts. For the underground parking levels, the high deformation zones are due to the number of load transfers from the walls to the towers to the columns and the parking levels. After the slab was analyzed, the check for punching shear was adequate, the rebar detailing was produced. Moving forward, this is an example of our podium level. This floor had to be checked thoroughly due to the complexity in the columns and the layout. The slab was processed using a finite element analysis to obtain CSA evaluations, which, as shown here, passed all the critical checks, including punching shear. And then the rebar detailing was obtained as well. Lastly, the residential level had to be checked thoroughly due to the corner columns, which are critical for punching shear failure. Working alongside my colleague, We modified the column dimensions to proceed to a passing punching shear check. The details of the building slabs was produced by SAFE, in addition to the scheduling of the bill of quantities and the scheduling of the rebar. Moving forward, my colleague Somar will present to you our column design.
Thank you, Michaela. Our column design process has been summarized in this slide. We started from taking all of the applied loads on our columns from ETABS, and then we use these loads in a pre-made sheet in Excel to get the proper dimensions and require reinforcements. Then we use this output from Excel to draw our sections in Revit, and then we double check our design in Robot. What our columns has been checked on is shown in this slide. The cylinderness first, the axial load, compression, and the applied moment, as well as the tensile load, if any, govern. The first thing we started with is checking the cylinderness by using this equation, where we can see that this equation is correct for all our columns and indicate that all our columns are short. Then for the type column, we use the equation, this equation, but for the spiral column, we use the second equation, as you can see. However, in both cases, we made sure that our column's resistance value is greater than the applied load. In the next slide, I am showing the columns that has been designed in more details, as this video shows the column location in our building. The first step was designing the column under compression by using the shown Excel sheet, where we input the column's height and dimensions along with the concrete strength, which give us the output, as you can see in this sheet. And then the next sheet, yep, as you can see, the column is short as well as it's safe under the applied compression. Also, there is this, also the requirements for the reinforcement are verified, as you can see as well. The next slide shows extra information that we had to add to the Excel sheet to work with the previous sheet and generate the interaction diagram that's showing in here. And you can see the column is pretty safe. The final detailing of our column, as you can see with the dimensions and the requirement rebars and ties in this slide. By coming back to the same short video that has been shown early, we can see that our column is going to look like how it's going to look like as a part of the building. And by isolating it, we can see another 3D view showing the detailings of our columns that has been done by Revit. Another two columns has been designed as well, as we are going to see. The first one is from the ground level and with a realistic horizontal section that you can see done by Revit as well. The last column to show is in the part MP2 with the detailing cross section along with a 3D model that's showing in here as well. Now I'm going to pass it to my colleague Ryan, who's going to be presenting the shear walls and our lateral analysis.
Thanks, Omar. So this is a large building with over 1,000 walls. So we came up with a very streamlined process using ETABS and Excel. For seismic design, the building was classified as conventional construction, and we used the ductility and overstrength factors of 1.5 and 1.3. This is a flow chart showing the algorithm we produced. The 5 items in blue shown here are the only user inputs. Basically, ETABS gave us a list of over 60,000 lines of forces. We made an Excel sheet that then indexes them and then assigns each index number with its wall geometry and concrete strength that we programmed into the sheet. And it uses this information to calculate the stresses and forces in each wall. Then it selects the critical load combinations and the design forces for shear, tension, and compression. So 60,000 lines is then reduced to 1,000, which contains all the design loads and wall geometries, and they're then re-indexed so that the design can then be carried out from a drop-down list. So simply by selecting a wall, all the design data is auto-loaded. You choose your reinforcement sizes, and all the calculation and code required checks are then performed. And if something fails, it will flash red, and if it passes, it will flash green. Once it passes, it's then sent to a schedule sheet, which tracks all the designs and calculates concrete and steel for costs. The result of all of this is typical shear walls are 300 millimeters thick. Select walls below the 9th floor range from 400 to 600 millimeters thickness. Based on the RD factor of 1.5, where horizontal anchorage is used for type 1 with standard 90-degree hooks or inverted bars. And based on our analysis, the stresses in the shear walls are almost exclusively in compression, with negligible tension between the middle stories of the high-rise structure shown in this image. While the upper stories experience considerable tension stress, this This is because the code requires large lateral forces at these top stories. And since there's minimal gravity loading up here, certain load combinations will produce quite a bit of tension. And conversely, we see tension below the 12th floor again, as moments of shear begin to gradually increase as you move down the structure. So the center compression zone of the upper stories is governed by minimum reinforcements, and it's approximately between 12th floor and 40th floor, because all the load combinations yield compression stress here. For shear design, the factored wind load was compared to the factored seismic load, which was multiplied by the RDR knot factor as required for a seismic design. A typical shear wall shown here is 9.5 meters long, 300 millimeters thick, and it's continuous from the 9th to 47th story. The tension stress at the 47th floor was calculated, and an equivalent tension force was equated to find the area of steel required. The wall shown here required 6 30M bars at each end, spaced at 150 millimeters, and tied with an tie spaced at 300 millimeters. The gravity loads are minimal up here, so minimum distributed reinforcements are provided, and minimum shear reinforcements are adequate as well. And below this, you see the basic design for the minimum reinforcement walls, which are in the compression zone of the building we talked about earlier. There are several wall column transfers in the building. The most notable is at the 7th and 8th floors. Here you can see a new wall that's introduced at the 9th floor to the typical floor plan to prepare for this transfer. And then at the 8th floor, there's a transfer from shear walls to columns, and we found an increase in wall thickness was required for several walls here. And then at the 7th floor, there's a significant change in the building geometry, and it transfers from columns back to shear walls. So you can see from the deformed shape of the building that this creates tension in some walls, requiring heavy concentrated reinforcement shown in the design here. Here's a quick overview of the ground floor elevator core, showing the planned cross-section of elevation view. Minimum vertical reinforcements are adequate in this wall, but heavier horizontal shear reinforcements are necessary to resist the factored base shear. For our lateral analysis, we had to consider the question, is the concrete cracked or uncracked? And if so, where is it cracked? ETABS does not know, but the code does require us to consider an uncracked section as having 70%, and cracked sections having only 35% of their gross section stiffness. In order to determine this, we adopted an iterative approach by looking at sections of the building based on their concrete strength and their associated tensile stresses from our analysis. To show you this process, we'll look at floors 7 to 13 shown here. First, we isolated these walls in ETABS to display the shell stresses from analysis. The stress limits on the spectrum shown below were set to be below between 0 and the modulus of rupture of the concrete strength associated with the walls. So anything in purple represents compression, and anything in dark blue represents the cracking point of the concrete walls. Walls shown in blue are considered to be cracked, and all other colors are considered as uncracked, and the respective factors are then applied. So obviously, if you start cracking some walls, it's going to reduce the stiffness of the structure and cause a bunch of other walls to crack. So this became a very long and iterative process. The result of doing this led to an approximate increase in our building period of 10 to 15% when we went from uncracked to cracked. You can see in the animations here how the building will behave under load. The largest of these periods is the y direction of about 5.3 seconds. Here you can see an elevation of the building showing its lateral displacement, and in the graph on the right, you can see the total displacement of the building was found to be 134 millimeters in the x direction and 265 millimeters in the y direction. For drift analysis, the MDCC requires seismic drift values to be multiplied by the ductility and overstrength factors and divided by the importance factor, which is 1 for this building. So the left graph shows the maximum inter-story drift for seismic loading while considering these added factors, and you can see that we're well below the seismic drift limit. And for wind, the MDCC requires the maximum inter-story drift to be taken as 1/500th of the story height. And in the graph on the right, you can see that the drift in both x and y directions are in fact below this limit. Moving forward, my colleague Matthew will present to you our final foundation design.
Thank you, Ryan. So as you know, we have a very tall building, and this building is situated on bedrock. So we have a high bearing capacity of 7,000 MPa for ULS and 5,000 MPa for SLS. This led us to design the foundation as spread footings and continuous footings. Now we have a very minimal dimensions and X and Y direction of the footing. However, we're governed by punching shear, which allowed us to design the deep beam foundation using a compression fan strut and tie method for stress distribution. As well as we have the lateral earth pressure coefficients from the borehole logs as 0.4 for the soil layers above the bedrock and 0.2 for the bedrock. Now, for the foundation design, we have this flow chart. We created our ETABS model from all the architectural drawings. We input design loads, as mentioned before, and we labeled the piers and columns to get the forces. After we got these forces, we exported them to Excel. This allowed us to determine the minimum dimensions, which was usually covered by the SLS capacity. After we checked shear in both one-way and two-way, and this allowed us to determine the minimum height of the footing. Now, after we got the minimum height, we had to check the compression depth. Now, this was a very tricky process. We had to limit the compression area to the code standard, and this required a cubic equation to solve for the compression depth, which we made in Excel using the solver function. After that, we had our moment arm, and we found the tension tie reinforcement, and then we were able to check the critical compression strut resistance, and we then checked if that was adequate for the development length. All of these were exported to a table, and they were put into Revit for detailing and the drawings. We repeated this 40 times for all of our foundation. Here's two examples. One is the exterior wall, and the other one is a typical spread footing. Now for the basement wall, we used the pressure coefficients as the soil went down. So did the force increase, and we modeled this in SAP. We took the critical area, which had the highest moment in shear, and we designed our walls based on that. It turns out that was just minimum reinforcement for the lateral earth loads. So 15 M-bars were needed at 200 millimeters center to center. Now I'll pass it off to Vahid for the final cost analysis.
Thank you, Vahid. You've been able to see our efforts and skill in this project overview. These are some of the references Noble used in our design. From everyone here at Noble, we would like to thank you for your time and give a special thanks to Dr. Mercer and our client, Dr. Blonsky. We would like to conclude with one final thought from our colleagues. This project emphasizes the importance of developing our skills with different structural analysis softwares in addition to interpreting and navigating building codes. We hope you enjoyed our presentation, and we're open for questions now. Dr. Mercer.